Assalamualaikum. We are from Group 10. We are going to present our group project about Mathematics for Engineering Technology 2. My name is Wan Muhammad Nur Hazim Ilya bin Wan Hussein. My matric number is CN240043 and my team member is Shavitra, daughter of Sugumaran. Her matric number is CN240203.
Good morning, everyone. I'm Shavitra. Here today, I'm going to talk about our maths project, which is about differential equation. Differential equation are important mathematical tools used to solve engineering problems that involve changing system. In this project, we study two practical problems that show how differential equation can be applied to real situation that engineers might face. The first problem look at Newton's law of cooling using a thermometer. We wanted to find out how long it takes for a thermometer to cool down from 45 degrees Celsius to 35 degrees Celsius. When it's moved from inside the house to outside, where the temperature is 30 degrees Celsius, this type of problem is useful for understanding how temperature sensor works and how long they need to give accurate readings in different environments. The second problem involves a mass spring system with damping. We have a 2 kg mass attached to a spring constant 18 Newton per meter with some resistance from the surrounding medium. 12 multiplied by, and the mass starts 4 meters below its normal position and is released with an upward velocity of 5 meters per second. This kind of system appears in many engineering applications like car suspensions, building designs, and machinery that needs to control vibration. We use different mathematical methods to solve these problems. For the cooling problem, we use separation of variables since it's a first order differential equation. For the mass spring system, we tried two approaches, the characteristic equation method and Laplace transforms. This help us check our answers and understand how different techniques can lead to the same solution. Both problems demonstrate how mathematics help engineers predict and understand system behavior, which is essential for designing effective solutions in real world applications. For the methodology part, our approach to solving these problems involved several steps to make sure we understand the physics behind the mathematics and got accurate results. For the problem setups, problem number 1, thermometer cooling. This involves a first-order differential equation using Newton's law of cooling. The equation dt over dt equals to negative k in a bracket T minus by m close bracket describes how the temperature T changes over time T, where m is the surrounding temperature and k is a constant that depends on the specific thermometer and condition. Problem number 2, mass spring system. This is a second order differential equation. 2x plus by 12x plus by 18x equals to 0. This equation includes the mass 2 kg, damping 12x, and spring force 18x with specific initial condition. For the solution methods, for the cooling problem, we use separation of variables, which is the standard method for this type of equation. This involves separating the temperature and time variables, then integrating both sides to find the general solution. After that, we applied the initial condition to find the specific solution. For the mass spring problem, we solved this using two different methods to verify our answer. Characteristic equation method, we assume a solution of the form E RT and substitute it into the differential equation. This gave us a quadratic equation to solve for R, which tell us what type of motion the system has. Laplace transform method. We converted the differential equation into the S domain, solved the algebraic equation, then transform back to get the time domain solution. For the tools and verification part, to make sure our calculations were correct and to better understand the results, we used several computational tools, which was Wolfram Alpha for creating graphs and checking our mathematical steps. Second is Symbolf for verifying complex algebraic manipulation. And the last one is manual calculation with cross-checking between team members. For the teamwork approach, we divided the work among the team members but make sure everyone understands all parts of the project. We met regularly online to discuss our progress and help each other with difficult parts. Likewise, each person's work was checked by others to catch any mistake. Newton's law of cooling. Thermometer problem. Problem statement. A thermometer is moved from inside the house out to the deck when its temperature has reached 45 degrees Celsius. If the outer temperature is 30 degrees Celsius, how long did it take the reading on the thermometer changing to 35 degrees Celsius? Use Newton's cooling law. dt over dt equals to negative k in a bracket T minus M, where T is the temperature of the body, M is the temperature of the surrounding medium, and K is a constant. The given information is initial temperature was 45 degrees Celsius, outer temperature is equals to 30 degrees Celsius, target temperature is 35 degrees Celsius. The equation is the same equation, dt over dt equals to negative k in a bracket T minus M. The solution for this problem are starting with Newton's cooling law. dt over dt equals to negative k in a bracket T minus 30 degree. Using separation of variables, dt over t minus 30 equals to k negative k dt. Integrating both sides. Integrate dt over t minus 30 equals to negative k dt. And then in magnitude, t minus 30 equals to negative kt plus c. This will give us general solution, which was T minus 30 equals to Celsius by in a bracket negative kt. T in a bracket T, which is a time, equals to 30 plus C E exponent by in a bracket negative kt. Applying the initial condition T in a bracket 0 equals to 45 degrees Celsius. 45 degrees Celsius equals to 30 plus Celsius by 0. C equals to 15. So our specific solution is T time equals to 30 plus 50 exponent by in a bracket negative kt. To find when T equals to 35 degrees Celsius, and then 35 equals to 30 plus 15 exponent by in a bracket negative kt. 5 equals to 15 exponent by in a bracket negative kt. Exponent by in a bracket negative kt equals to 1 by 3, and then we will get negative kt equals to ln in a bracket 1 by 3 equals to negative ln in a bracket 3, t equals to ln by negative 3, then by k. So the answer, the time needed is t equals to ln 3 by k, where k is the cooling constant. What does this mean? The thermometer cools down following an exponential curve. The actual times depends on the value of k, which would be determined by the specific thermometer and environmental conditions. Since ln 3 equals to 1.099, if we know k, we would calculate the exact time. See that the cooling solutions graph. The answer is T equals to ln in a bracket by K. The cooling follows exponential decay. That's all.
I will continue our presentation. We will be exploring a practical engineering problem using differential equation, analyzing a damped oscillation system. We have a mass spring system with the following parameters. A 2 kilogram mass attached to a spring constant of 18 newtons per meter, damping coefficient of 12 newton second per meter, initial condition, the mass start 4 meter below equilibrium with an upward velocity of 5 meter per second. This setup gives us a differential equation which we will solve using multiple methods to verify our solution. To solve this differential equation, we will use two different approaches that demonstrate the power of mathematical verification. Method A use the homogeneous equation approach, also known as the characteristic equation method. We assume a solution of the form x equal to exponent power of rt. This gives us the characteristic equation r square plus 6r plus 9 equal to 0. Solving this, we will find repeated roots at r equals to negative 3. Method B applies the Laplace transform method. We, trans we transform the differential equation into the S domain, solve the algebraic equation, then apply the inverse transform to get our time domain solution. Both methods will give us the same answer, that which is x t equals to 4 plus 17 exponent power of negative 3 t meters. Okay. Now let's examine our result and understand what they mean physically. Our solution is xt equals to 4 plus 17t exponent power of negative 3t meters. The verification shows that both solution methods give identical results, which confirm our mathematical accuracy. Looking at the graph, we can see the physical behavior. The system exhibits critically damped motion. There is no oscillation. The mass returns smoothly to equilibrium. This represents the fastest possible return to equilibrium without overshooting. The physical meaning of the physical meaning is crucial for engineering application. This type of response is often desired in control system where we want quick settling without oscillation. This problem demonstrates the importance of both computational tools and collaborative verification in engineering. The tools we use include Wolfram Alpha for symbolic computational and verification, also with graph, Symbolab for step-by-step solution method, manual calculation to understand the underlying mathematics. Our approach involves dividing tasks among team members, each person verifying the others works collaboratively. Cross-checking results using multiple solution method. This collaborative approach ensures accuracy and builds confidence in our engineering solution. Let's conclude by highlighting what we accomplished and learned. Key learning outcomes. Differential equations are powerful tools for solving real engineering problems. Multiple solution methods provide essential verification of our result. Mathematical analysis help us predict and understand system behavior. These skills are essential foundation for engineering design and analysis. For future application, this foundation prepares us for advanced engineering courses. The problem solving approach applies to circuit, heat transfer, fluid dynamics, and control system. Today works demonstrate how mathematical theory directly applies to practical engineering challenges, giving us the tools to design and analyze real-world systems effectively. That's all from us. Thank you.